Good afternoon. I hope you guys are at home having a nice break from school. This is a quick supplement in order to help you figure out how to work through balancing a redox reaction, specifically in acid conditions. And I really like these problems because they tie together everything that we've done for balancing reactions. It talks about conservation of mass, talks about identifying reduction and oxidation, so transfer of electrons, looks at balancing atoms and charge, and then it brings it all together through how many total electrons are transferred. So the goal for this short supplement is going to be for you to be able to balance a redox reaction in acidic conditions, and I want you to please pause as we go through this and work on the questions that I suggest on your own, and then resume play in order to see how we do it together. So the problem that we're going to work on together is dichromate interacting with iodide to generate chromium 3+ ions and iodine. And notice that this is the net ionic equation for the reaction, and we've already removed spectator ions. So the first thing that we're going to do is look at this reaction and try to balance it. So go ahead and try to balance it, and then think about what problems we initially have. I imagine that what we first find is that we don't have oxygen on both sides, so it becomes a bit more challenging to balance. So go ahead and think about which one of these chemical species is oxidized and how you determine that. So pause the video and determine what species is oxidized. Now, in order to answer this question, I really hope that everyone paused and identified the oxidation number for every single element on both sides of the reaction, on the reactants and the products. If we look at the most challenging one, the dichromate, Cr2O72-, we can assume the rule that is typically held, that each of the oxygens is a -2 oxidation state. There's 7 of them. Then that means that we have a -14 oxidation number there. We know that it needs to add up to -2. So that means that we have +12 in the rest of the polyatomic ion. And that +12 has to come from 2 chromiums. So that means that our chromium has to be +6 for each one. There are 2 of those, so we have +12, and we can confirm that +12 minus 14 sums up to 2-. Okay, so we have +6, we have -2. Iodide, the formal charge is going to be equal to the oxidation number in this case, so this is a -1. If we look on the right side, chromium 3+, oxidation number is equal to the formal charge because it's an ion with only one component again. And then iodine is molecular, so it has a 0 oxidation number. So then we want to look and say what was oxidized. Remember, oxidized is losing electrons as oxidation. I did that backwards. So if we look from left to right, I'm going to use a blue pen. Chromium looks like it gained electrons, so that means that it is reduced. And then the thing that looks like it lost electrons, went from an oxidation number -1 to 0, is losing electrons, so that is oxidized. Okay, so the thing that was oxidized, a species, was iodide, I-. So now we're going to try to go ahead and balance this reaction and then determine how many total electrons were transferred. So the first thing I want you to do is I want you to pause the video and divide this net ionic equation into 2 half reactions. Go ahead and pause now and resume when you're ready. The 2 half reactions are going to be the reduction reaction that we described, which is chromium is gaining electrons. So that means we're going to have dichromate reacts and gains electrons in order to become chromium 3+. Then the oxidation half reaction is iodide loses electrons and becomes I2. But this is not balanced. Not only is there a difference in the formal charge on both sides, the number of atoms, but it also has some atoms that don't even exist on both sides. So whenever we have this in acidic conditions, here are the steps we're going to go through. the first step is balance all non-hydrogen atoms and non-oxygen atoms. So in the reduction half reaction, go ahead and pause and do this for both reactions. What I imagine that you'll see is in the top reaction we have 2 chromiums on the left side, 1 on the right. It means we need to have 2 Cr3 pluses on the right side. For the oxidation half reaction, we have 1 I on the left, 2 I's on the right. So we need to have 2 iodides. Okay, that was easy. So now comes the tricky part. The tricky part is next. We leave oxygen to second to last, hydrogen to the very last, and then electrons we do after we balance the entire reaction. So now what we're going to do is we're going to add water to the side of the reaction that has fewer oxygens in order to make both sides equal. If you notice here, we have 7 oxygens in dichromate. That means that in order to balance just the oxygens, we need to have 7 waters on the right side. And I think I have that animated to show. In the bottom reaction, we don't have any oxygens on either side, so we're fine. But now I hope that you notice, well, isn't this kind of silly? Because now we have hydrogens on one side and not the other. So we solved the problem with the oxygens, 7 on both sides, but now we have hydrogens. So then the last step for balancing atoms is now we have to add H+, because remember the initial problem said we are in acidic conditions. Acidic means H+. So we're going to need to add H's to the left side in the form of H+. On the right side here we have 7 waters, each one with 2 hydrogens. So that means we need to add 14 H pluses on this side. We should write aqueous as well. And I think that that's a little more clearly animated here. Great. So now we're balanced with chromium, oxygen, hydrogen. Second reaction, just iodine. And then the last thing we have to do is what about charge? So now I need you to go look at both of these half reactions and determine what the relative charge is on both sides of the reaction. So let's go ahead and add up on the left side of each of the reactions and the right side of each reaction. Go ahead and pause and determine what those overall charges are on both sides. When we do that, we're going to find that the left side has 14 H pluses, 1 dichromate, which is a 2 minus, so that means on the left side we have a total of plus 12. On the right side we have 2 chromium 3 plus ions and water, which has no charge. So that means we have plus 6 on the right. How do we get these two sides to be equal? And I hope that from doing a bit of redox chemistry we know that we can put electrons, which are negatively charged, on one side or the other. Remember, we can only add them, we can't subtract electrons. It doesn't exist. So in order to make the left side and the right side equal, we're going to have 6 electrons on the left side as a reactant. Now the bottom reaction, we see that we have 2 iodides, so we have 2 minus on the left side, we have 0 on the right side, so that means that the right side of this equation needs 2 electrons in order to be charge balanced as well. So now we have both of our half reactions completely balanced with everything from atoms to charge. The last step that we need to do is determine how many total electrons were transferred in this reaction. Go ahead and pause and resume when you got your answer. I hope that what we're looking at now is we say that in the first half reaction, in order for this reaction to proceed, once 6 electrons need to be accepted. In order for the second reaction to happen, once 2 electrons are given up. So that means that the top reaction can't happen unless we have 3 times the second reaction occur. The other way to say that is that we have 3 times the second reaction happening every time the top reaction occurs. In order to generate those 6 electrons that are used up by the reduction reaction, the oxidation reaction has to happen 3 times. So that means that we have 6 iodides reacting in order to form 3 iodine and releasing 6 electrons. So the answer to this question is that 6 electrons are released every time this reaction proceeds. Or transferred, I should say, not released. They are transferred overall. That means that the iodide loses them and the chromium gains them. The last step we have to do is we have to take our 2 half reactions and we add them back up together. We basically do this by putting a line underneath here. We put a little addition sign and we add up everything on the left side. That wasn't quite everything on the left side. Everything on the left side, and arrow, and then everything on the right side. So we're going to put our arrow in the middle here, everything here, everything here. And the reason that we do this is to make sure in the end that on the right side we have the same number of electrons released as we do on the left side that are gained. So we can write this all out. We have our final balanced chemical reaction for this in acidic conditions. So I hope that by watching and participating in this short supplemental that you are now able to think about the steps needed in order to balance a reaction, redox reaction specifically, in acidic conditions. Make sure that you follow those steps precisely. If you try to balance with electrons first, or you try to do hydrogens with protons first, it doesn't work. Good luck on the rest of your homework, and I'll see you in class on Tuesday, where we'll be working on another one or two of these.